next lesson on resistivity, and it deals with how we look at a property of a material, how much resistance it presents. This is a material property, not a dimensional property, a material property. A little bit like how Young's modulus is a material property, not a dimensional property. Hopefully I'll explain that a bit more thoroughly in a minute. Okay, let's take our circuit. First a nice simple circuit and have a simple resistance in there. Let's say I've got an ammeter that's registering, well, let's try and work out what it's registering first. If we have 6 volts and 20 ohms. First of all, of course, we will use Ohm's law, and we say that this is 6 over the 20, which gives us 0.3 amps. Great. Now, of course, resistors have a range of values, and the range of values can be determined by certain factors. If we imagine to ourselves that we have a piece of wire, and I'm going to just increase the size of this piece of wire. So we're thinking about what we've got here. Really, what it is, it's a series of it's a series of electrons flowing through, and those are trying to avoid these positive ions. I think that's what we learned at GCSE, and that will serve us well in this description as well. Now, of course, first things first is, obviously, what's going to increase the resistance or decrease the resistance, conversely. Now, you know these are bumping into the positive ion lattice as it goes through, so actually length of resistor will have an effect. And I think you know that anyway, because the longer a piece of wire is, the greater the resistance, so you know it's proportional to its length. I like to use the analogy of people, electrons flooding out of a football stadium. Imagine they're all getting through one turnstile. Now, if you opened up another turnstile, or you increased the area, then you would allow that football stadium to empty quicker. So we know that area is going to have an effect. But all of these resistors, the range of values that they have, aren't dictated by the size of the resistor you're using. The third effect is obviously the material type. Because you can have hugely different resistors, all similar sizes, but with greater or lesser amounts of resistance. So the material must have an effect upon that. And also then there's sort of subtler effects, and I put them as sort of for things like temperature, pressure, etc., etc. But actually we don't need to worry too much about those effects at AS. But you can imagine if these ions were to start vibrating with temperature, then they'd start to affect the resistance, etc., etc. So how do they all come together? Well, like I said, we have proportionality with length, because the longer it is, the greater the resistance. So our resistance is going to equal, it's going to be proportional with length, but inversely proportional to the area. If we have a greater surface area, then we're reducing the resistance because there are more effective paths for it to follow through. And of course, all of these are linked. The constant proportionality is called the resistivity. So this part here is the resistivity. And it's given that symbol ρ. It's a material property. So that means it doesn't matter how long the material is or how wide the material is, the resistivity dictates how much resistance a certain material will present. And it's measured in ohm meters. I hope you can see that. Ohms on this side, meters on the top. Meters squared at the bottom means that meters come up and we can get ohm meters. Saying how many ohms does 1 meter of it present? Okay, so that's hopefully quite straightforward, resistivity. I mean, there will be practicals that we do in order to determine these two. So these are practically based. But once you have that under your belt, then the rest is quite straightforward. Quite a lot of mathematical manipulation, especially considering the areas, pi r squared. mean that we're going to start to have to get some serious rearrangement going. Okay, first things first, let's give it a question and see how you get on with this. Here is a very small little piece of copper printed on a circuit board. We are going to have the dimensions of it running at 12 millimeters long, and then we get a 2.5 millimeter width and a 1.5 millimeter height. We're going to connect this across a 5-volt battery, and what I'd like you to work out for me is the resistance that's presented if I tell you that the resistivity of this material is 1.3 times 10 to the 5 ohm meters. So first of all, can you tell me the resistance, and then can you tell me the current that will be flowing through this circuit? If you think you know, hit pause, because here comes the answers. Okay, first of all, resistance is rho L over A. We know what rho is. L is quite straightforward, 12 millimeters, but we need to do something with the area and work that out. So we get resistivity first. The length, 12 millimeters. Now be careful here. And our area, it's 1.5 millimeters by 2.5 millimeters. And that gives me a grand total of 4.16 times 10 to the 8 ohms. That represents quite a large amount of resistance. And then if I wanted to carry that through and I worked out the current, the current is the voltage divided by the resistance, which gives us 5 over 4.16, 10 to the 8, giving us, well, that's approximately, because 5 over, that probably knocks itself out, so it's approximately 10 to the minus 8 amps. Okay, so far so good. What we'll do next is we're going to have a look at how to manipulate and rearrange it to get the lengths and the areas. So here comes our next problem. Let's imagine that we have a piece of copper wire, and this copper wire is used to connect a car battery to a starter motor. A car battery, of course, takes a huge current to turn over the motor, 150 amps it goes through. And we wouldn't expect any much difference in the potential difference. I mean, it's a little bit weird here because it's not across a battery, but the drop in potential difference, the energy per coulomb lost as it went through this piece of wire, we wouldn't expect more than 0.13 volts across it. So if that's the drop, I suppose the question is, first of all, what is the resistance that this piece of copper presents? The second question is, if we know the resistivity of copper, 1.6 times 10 to the minus 8, and the length is 0.24 meters, then what's the diameter of this wire in order to provide that much resistance? Okay, if you think you know the answers, hit pause and you can give them a go. Otherwise, here comes the answers. Okay, so first of all, the resistance. This is going to be the voltage divided by the current, or the drop in voltage, which is 0.13, divided by the 150, a huge current going there, gives us 9 times 10 to the minus 4 ohms. That's not much current at all, which is good because you need to deliver such a high, that's not much resistance, which is good because you need to deliver a very high current flowing through there. A little bit trickier with the diameter. Let's first of all write out our equation. We need to rearrange it to secure the area. So what happens is you move the area up there, exchange places with resistance. Okay. We also know that area is pi r, the radius being the diameter over 2 squared. So rho L over r, that squared brings us to 4 over pi equals d squared, so we square root that. So let's substitute in the values. 1, 4 by 1.6 times 10 to the minus 8. The length of it is 0.24 meters. And now we know the resistance 10 to the minus 4. Root all of that, and I'm guessing it's approximate. Let's say that just cancels itself. 10 to the minus 4 cancels, bringing that to the minus 4. 1 by a third of a 1 gives you a third times 8. 10 to the minus 4, it's going to be in the 2s, which brings it to about 10 to the minus 3. That's going to be about 2 times 10 to the minus 3 meters. Very, very small diameter, though quite thick nonetheless. I mean, if you think about wire, you're on 2 millimeters diameter, so that's quite thick. Okay then, let's work with another example for you, so you can rearrange it in one last way. And let's say the diameter of wire is 2 times 10 to the minus 4 meters. The resistivity is 4.2 times 10 to the minus 7 ohm meters. Let's say that resistance is 25 ohms. What length is required to provide that much resistance from this type of material? If you think you know, your chance to give the answer. Hit pause, otherwise here comes the result. Okay, resistance is rho, L over A. Of course, we want L isolated, so let's move that around. Let's substitute in our values, but this time, of course, remember, we need to diameter times 10 to the minus 4 into radius, square that up, divided by, and that gives us a grand total of about 1.87 meters. Super easy. Okay, the last one's going to be a question on proportionality. Let's imagine we have this putty, this conductive putty, and it has a length L, an area A, and it presents a resistance R. Now let's imagine we double that putty to 2 lots of the area. What would be the resistance that's now presented? So we've increased it to twice the area. Now this appears to be easy at first sight. However, what we need to bear in mind is that not just the area has doubled, because we've got the same volume of putty, so therefore we've effectively halved the length. Now if we look at those two considerations, our resistance is rho, in this instance, rho L over A. And now in this instance, we've got half the length, but twice the area. So that presents us with half the rho L over A all over 4. So therefore our resistance is going to be a quarter of the first resistance. And that's quite a famous type of question they like to talk about. Good, okay, so that's resistivity pulled together quite neatly. Let me give you one other question which hopefully we can start drawing together some parallels between the other subjects. I'm not sure whether you're familiar with car rear windows. They have these elements on them, tiny bits of wire that run back and forth across the window to help demist the window or to de-ice it. And I'm going to write 1, 2, 3, 4, 5, 6, 7, 8 of them, and we're imagining them on the back window. Now there's ways in which we can, well the brief, first of all, was that these are 48 watts needed and 12 volts for this entire system here. And we're going to try putting it together in a parallel and series combination and work out for both, firstly, the current that's drawn in a parallel and series combination, the resistance of each, in the parallel and series combination. And I suppose it would be helpful if you work out the current, total current, and then the individual current. Okay, so in the first instance, I want this to be with parallel, And in the second instance, we'll run series. Now, if you think you know what's happening, hit pause, and yes, hit pause, give it a go. Otherwise, here comes our solutions. Right, the parallel combination is simply 8 of these, 1, 2, 3, 4, 5, 6, 7, 8, all attached to a battery supply of 12 volts. 48 watts implies that the current is going to be the power divided by the voltage. I hope P is IV is something you're familiar with. So therefore 48 over 12 gives us our 4 amps that will be flowing in and out of the battery. I've drawn that the wrong way around. Draw it that way. Now of course I've got 8 branches going on here. So therefore if 4 amps totally, that means each branch, individual let's say, is going to contribute an eighth of it, which is 0.5 amps. Okay, now, because it's in parallel, I know across each of these we have 12 volts, and I know that 0.5 amps is travelling through, so the resistance is the voltage divided by the current, which is in this instance 12, 0.5, giving me 24 ohms to each element. Right, now of course we could connect in series. Let's count 1, 2, 3, 4, 5, 6, 7, 8. And in this case now, I've got 12 volts. The current here is once again power divided by the voltage, 4 amps, but in a series circuit the current is the same throughout the circuit, so I know that in all of them I've got 4 amps, drawn the wrong way again, 4 amps flowing. So the individual is going to be 4 amps. But what about the resistance? Well, this is cunning here, because before we divided up the currents, but now because there's 12 volts and 8 elements in series, effectively I have 8 lots of resistance from top to bottom. And of course 12 over 4 gives me 3 ohms. So my total resistance is 3 ohms between edge to edge, but I've got 8 little elements. So the resistance is going to be 3 over 8, which is 0.375 ohms for each one. Quite cunning. Okay, let's take one of these little elements and say that's 0.75 meters. Let's say the width is running at 3 millimeters and there is a depth of 0.12 millimeters. What other information will you need to know? You need to know the resistivity of this material is 1.8 times 10 to the minus 7 ohm meters. So, no, that is the answer. Apologies there. Just in case you didn't see that. What is the resistivity of the material that these are made out of? Okay, even if you saw the answer, let's try and work this one through. If you think you can do it with all the information provided, go for it. Otherwise hit pause. Otherwise here comes the answer. Right, we know resistance is rho L over A. The series setup is the one that we're interested in, so we're running at that type of resistance. So resistivity is going to be RA over L. Series 0.375 times the area, which is now 3 millimeters, by 0.12 minus 3, width in millimeters, divided by the length, which is 0.75, and that gives us, if I'm not mistaken, that'll give us 7.5 over 3.5, which is approximately, it comes to about a third, which cancels with that, give us 10 to the minus 6, so that's about 10 to the minus 6, including that one, 10 to the minus 7, to about 1.2, 1.8 times 10 to the minus 7 ohm meters. Hopefully that makes some sort of sense. Lastly, I will just show you how we do resistor networks or resistor combinations. So this can be very straightforward. Once again, a little bit of maths here. We can prove it with Kirchhoff's law later. I'll just show you briefly how we put them in series with each other. R1, R2. Our total resistance is R1 plus R2. I'm sure you're aware of that one. That's the easy one, and as many as you want to add. However, in a parallel combination, this can be as many as you want. R1, R2. That 1 over the total resistance is 1 over R1 plus 1 over R2 plus, and we carry on going. Now for the case where we're only using 2 resistors, then this can be simplified. 1 over R total, let's make a common denominator here. That means this needs to be multiplied by R2, add it to R1. And the whole thing requires inversion, so RT, so all of this inverts. R1, R2 over R1 plus R2. So that, for 2 resistors, is the equation for the combination. I suppose we could do a few examples if you want. So let's do one that's a little bit more complicated straight off the bat. We can do either algebraic. Let's do it algebraically. It's probably much easier. Let's say that's 3R, that's R, and this is 2R. What's the total resistor combination? I have to replace all of that by one resistor. What would it be? Well, we've got 2 in series and parallel, so let's combine those two. So in effect we have 4R in parallel with 2R. Now we can say to ourselves that the total resistance using the equation above is 2 times 4 over 4 plus 2, giving us 8 over 6, which is 4 over 3, 1.3 R. Really straightforward. And we can continue this complication all the way through. So I think, hopefully, that should be straightforward, those topic areas. Good, there it is.